Hello, everyone. I thought I'll start, so that means that we're getting closer to the cocktail hour. I know, I don't have that on my mind at all. I really don't. I don't drink alcohol, actually, even though I'm Irish. Not anymore. Anyway, they're all asides. Next, we have multidisciplinary outlook of a future using space resources. And this is going to be moderated by Maher Kalaji, who is from the Asteroid Foundation. So I do hand the floor to you.
Thank you so much. Thank you so much, Lisa. It's a pleasure to be here again. The session is Multidisciplinary Outlook of a Future Using Space Resources. And I'll have to admit, I'm really guilty. I only started looking at the speakers last night. And then I realized that this is really a truly multidisciplinary session. It's covering a whole wide range of topics. And when I started looking at them, I didn't even think they were space-related. I mean, you don't have to be a specialist here to understand the challenges our next four speakers will talk about. But you also have to admire the methodologies that they use to address these challenges. They vary from nuclear fission to fungi to fuel sloshing inside a tank to finally buildings in outer space. And I think you will be really amazed by what these guys are doing. And I'm going to ask them to stay here after they're finished their talks in case there are general questions at the end for the group of people there. The first speaker on the program has apologized that he could not be here. He's got some viral infection. So we're going to jump to the second speaker on the program, which is Dr. Hannah Sargeant. She is from the University of Leicester. She calls herself a planetary scientist, and she did her PhD in planetary science as well. She works on some really interesting topics, and she, in her PhD work and her postdoctoral work, she worked on the LoveMe-X rover team, and she was working on a mass spectrometer, developing the mass spectrometer design there. She is a lady or a scientist who has been awarded the Amelia Earhart Fellowship in 2019. Correct me if I'm wrong. And she has been listed in Forbes 30 under 30 for science and healthcare in Europe. Today she'll be talking about a really interesting topic, which is ISRO applications of European radioisotope power systems technology. The floor is yours.
My gosh, that was quite the introduction. Thank you. Okay, so I'm basically here today to highlight some of the work that we've been doing at the University of Leicester to develop radioisotope power technologies within Europe, and just to kind of highlight to you all how you might possibly use them. Possibly? Yes. Okay, so I'll start off by summarizing some of the potential ISRU needs that radioisotope power could be used to address. So firstly, surviving the lunar night, those 14 days of cold darkness. So we could potentially use some thermal power to maintain battery systems until the solar charging can then resume. We then want to look at thriving in the lunar night, so using thermal and electrical power to operate during the lunar night. And this also kind of corresponds quite closely with permanently shadowed regions and operating within these really harsh environments when solar power isn't available. And then finally, potentially using radioisotope power for resource extraction in the form of thermal ice mining and potentially even higher temperature processes as well. I don't talk about those here, but these are kind of areas that we're interested in. So if you have any ideas, please come speak to me afterwards. So a little bit about the European Radioisotope Power Programme. So historically, plutonium-238 fueled systems are those that have been historically used in spaceflight, particularly in the US, but they have rather limited supplies. So you may have seen in the recent planetary decadal study, there are a lot of missions that needed some quite large radioisotope thermoelectric generators, or RTGs. But there just isn't enough fuel to make that happen. So actually, this is quite a bottleneck. There isn't the capability there to use this type of power system system for all of the missions that we want to achieve. And so plutonium-238, it has a half-life of around 90 years, so that means that the power output will gradually decline on the scale of a few years. You'll start to see that degradation in power output, but it has a thermal power capacity of about 0.5 watts per gram. Now, at the University of Leicester in the UK, we are developing RPSs using a different fuel, americium-241, and this is because it is actually a waste product from our civil nuclear power sector. So we have quite a lot of americium-241 available. The difficult bit is turning it into the ceramic fuel pellets, but that's why we are working with the National Nuclear Laboratory in the UK to help us achieve that and make those fuel pellets. And we are building all of the hardware to make the spaceflight system. So americium-241 has a half-life of 432 years, which means that the power output actually stays pretty constant on the scale of a few decades. So if you're looking sort of longer duration missions, your power outputs will be nice and consistent with this americium fuel source. But it does have a lower capacity, so we're around 0.12 watts per gram compared to that 0.5 watts per gram for plutonium. But as a comparison, I've just got here like a pretty simple plot showing if you had enough fuel of each to give you 100 watts thermal, you'll see that over the scale of a few decades, the americium-241 really holds its own. So this program is funded by ESA's European Devices Using Radioisotope Energy program, or ENDURE. And ENDURE will end Europe's dependence on foreign nations for radioisotope heat and power systems. Based on americium-241, ENDURE will open the outer solar system and other challenging planetary environments to European exploration. So basically, we want to be able to utilize radioisotope power within Europe. So at the moment, you can launch radioisotope power systems in the US, and there are launch pathways to enable that to happen. That doesn't quite exist within Europe, so we are working with the French regulator to try and make that happen so that we can obtain the required launch authorization and prove that our systems are safe to launch. So now I'm just going to summarize some of the systems that we have that we're looking to offer to the community. So first we have radioisotope heater units, or RHUs. And inside, so in the pink capsules, that's kind of showing that's where the fuel pellets will be. And everything else is purely for safety. So if anything was to go wrong, if a rocket blew up on the launch pad, there should be no release of radioisotope material. That's what all of these layers do. So you have your platinum cladding, which should, on impact, should not fracture, and it should just compress around the fuel. The aeroshell is there in case there is a re-entry scenario, so if something goes wrong on launch and this falls back to Earth, this should still survive, and there should be no release of radioisotope fuel. As a comparison, for those who are more familiar with the US systems that already exist, there is the lightweight radioisotope heater unit that they've been using. So that is a 1-watt system using the plutonium fuel, and our system is around a 3-watt thermal system. So I've just got a small table to kind of highlight this. So you've got about 200 grams for our RHU, and the lightweight RHU is around 40 grams. So in terms of opportunities, radioisotope heater units, we are looking to hopefully include one of our RHUs on the ExoMars lander. So this will enable the lander to operate for longer, so increasing the longevity of that lander life for a few days so that it can de-risk the deployment of the rover. So if there is anything that goes wrong or there's something that they need to troubleshoot, they have a little bit more time to enable that to happen. And it also gives us the time and the opportunity to work through the nuclear launch safety process with NASA and the Department of Energy. So the next system we have is a much larger European large heat source, is what we call it, and this includes 12 large fueled clads, which produces around 200 watts thermal. This is, again, kind of the same sort of scale in terms of size, but now because of the difference in fuel, we have very different types of systems now. So this is the US General Purpose Heat Source Module, the GPHS. So using the plutonium fuel, because it produces so these two systems produce on the order of the same amount of thermal power. So ours produces 200 watts thermal, the GPHS produces 250 watts thermal, but ours is much larger because the quantity of fuel is higher. Because americium does not have as much of a thermal power output as the plutonium does. So because we have to have more fuel, we also have to have more shielding, more cladding, etc. So the mass starts to increase. Now you can actually put these larger heaters into thermoelectric generators, so couple the heat source with thermoelectric conversion technology, and that takes around roughly on the order of about 5% of your thermal power into electrical power. So here on the left is our RTG in development. I think we're currently at around TRL 5. Comparing to the US systems, they actually, so our version only has one heat source inside, one European large heat source. The MMRTG, the multi-mission radioisotope thermoelectric generator, God, these are real mouthfuls. So the MMRTGs, they have 8 of their heat sources. So this is where you really start to see this scaling issue. So our RTG can produce around 200 watts thermal, 10 watts electric for about 10 kilos, but they are designed to be stacked, so they're designed to be modular if you wanted to have more. The MMRTG, about 45 kilos and gives you 2,000 watts thermal, but the amount of plutonium fuel required to build one of these is quite significant. So these are not going to be ready to supply many missions. So that's why we want to provide an alternative power source that could be utilized not just within Europe, but internationally. So potential use cases. So there have been discussions about the possible inclusion of a European RTG on Argonaut, perhaps. I also then started to look at how RTGs have been thought of or considered for use in ISRU applications specifically. I came across this one particular paper. There we go. One particular paper with which coupled the MMRTG to a thermal corer, so using the electrical power to operate the drill and the thermal power to actually thermally mine the ice from the regolith. But I haven't really seen much going on in the field of ISRU and using RTG, so I think there's a lot more work to be done here. There's a lot more opportunities that could be explored. I now want to talk about dynamic systems, so dynamic radioisotope power systems, or DRPS, and these use a power conversion technology, so taking thermal to electrical power using something like a Stirling generator, a Stirling converter. But because it has moving parts, this is slightly more problematic when you're talking about launching one of these systems in space. Because moving parts means things that could go wrong, it might require more maintenance. So these have never flown before. So Stirling converters have not flown, but it is the plan to do so at some point. So here we have some images of the ASC converters that are on test, I believe, at NASA Glenn. But there are a number of different Stirling converters out there. And we've actually been working with a few of these organizations. So we've worked with Aerojet Rocketdyne and we've worked with NASA Glenn and looking at coupling our ELHS, our larger heat source, to their dynamic converter technologies, just to see what could we produce. Because our thermal output isn't as high, we really need this extra from the Stirling converters to give us around 20% conversion, which is far more electrical power than you could get from your thermoelectrics. So we've been working with Aerojet Rocketdyne and NASA Glenn. So here's two of the concepts. We're actually working on a publication for this one on the right-hand side. And we're looking at around 110 kilogram power source, which could give you 800 watts thermal, converting 213 of that into electrical power. And then actually we worked with both of these organizations to look at potential applications, potential mission concepts that would benefit from this. So we looked at taking the Aerojet Rocketdyne dynamic power system and putting it into a ice mining rover. So this is a rover that could theoretically operate in a permanently shadowed region continuously. It would never have to go out into sunlit region to recharge. So that means it can traverse much further, kilometers perhaps, into permanently shadowed regions to really access those ice deposits. And we've done some thermal modeling to look at how feasible this might be, and it does look promising. So we have the thermal power from the power system going into a heater plate that is then directed onto the icy regolith below, and the electrical power to operate the rover itself. A similar concept this clicking might need a new battery. A similar concept was worked on as part of a compass study with NASA Glenn, taking that dynamic power system that we worked on with them to couple it to a Viper scale rover. And they compared it to the current operations and showed that it is feasible for to use this sort of power system compared to solar. So just really highlighting that we should be looking at this, and we want to be having discussions about how we can use our power source with your potential mission applications. Come on, one more slide. Okay, conclusions. So we have radioisotope power systems that are in development in Europe using americium-241 fuel. And we are hopefully looking to have our first flight opportunity on the ExoMars lander. There are a range of RPS available to provide stable heat and power for decades. And that's the thing that I'm particularly interested in, these long duration missions, perhaps deep space or prolonged operation within permanently shadowed regions. And yeah, looking to support on the moon, in particularly lunar night and PSR operations. So thank you very much.
Stay. Yeah. Thank you. I mean, this is really interesting. I mean, it's worth highlighting that we're talking about nuclear fission here, that it's not going to go off like a nuclear bomb or something like this. But I tried to look at the safety records of these things, and the only thing I could find was for plutonium initially, and it was used on the Mars rover. And there's an environmental impact assessment in 2000 and I can't remember, probably 2020 for the Mars rover. And there's a 1 in 2,700 chance that the plutonium used on that can re-enter back into Earth at the early stages or just as it hits the orbit itself. And actually, in 1978, Cosmos 954, I think, dumped about 54 kilograms of uranium when it actually failed and when it came back to Earth, and dumped it over Canada. Fortunately, the area was not heavily inhabited. There's hardly anyone in there. But these things still carry a risk with them. I mean, they are extremely efficient up there, and I think they are the way forward, but there's still some risks associated with them. Can you comment on that at all?
Yeah, so there is definitely hypothetical risk involved, and as you say, there are examples where things have gone wrong in for example, the uranium kind of being deposited. But there are actually examples because of the amount of concern that there is with these types of systems. People hear nuclear and they panic, and I get it. I used to do the same. But actually, these safety mechanisms that are included basically are there to we have to demonstrate that in every possible scenario, to a reasonable probability scenario, we do have to cap it eventually at something, but a reasonable probability that anything bad could happen, we have to prove that we can survive that, and there will be no release of fuel. There were actually examples of, I think when there was a radioisotope system, that there was a launch failure and the system fell into the ocean, and they actually recovered it from the ocean and were able to retrieve the fuel, open the capsule, retrieve the fuel, and use it in a future system because the containment worked exactly as it was supposed to. So no one is going to approve a launch without going through everything with a fine-tooth comb, and we plan to demonstrate that we meet every requirement.
Fantastic, thank you. Does anyone have any questions in the audience? There's a question over there.
Thank you. Hi, I'm Maarten Roes, a planetary scientist. I was just very curious to see that ExoMars might carry one of these things, perhaps. I thought ExoMars should have been on the surface of Mars by now. So are they making changes to the spacecraft still? I'm a bit puzzled.
So the lander, because I believe the lander provider has changed in recent years. It is now a US lander providing that system, and so that is still being worked on. Yes, not the rover. The rover itself is still. I think there might be lightweight ruse on the rover.
So the landing platform is being built in Europe now.
Right.
It used to be a Russian one, and let's say the launch will be provided by the US. That's the plan, and the RHU is going to sit only in a landing platform. On the rover itself, we will have US RHUs.
Yes.
That's the plan.
Thank you very much. You're still going to stay on stage in case people think of questions at the end for the group, and they'll all be here. There's plenty of water there, so help yourself. Okay, the next speaker, again, I have to think carefully of what I say about this, because I was having my dinner last night as I was reading the abstract here, and it talked about lettuce in the abstract. And again, it's a really fascinating subject which combines biology with metallurgy and a whole host of things. And the next speaker is Satinder Shergill, who currently works for Solstice Mining, which have a booth outside. But he's also doing his PhD, or completing his PhD, at the University of Cranfield in Bedfordshire, in the UK. He has also been, I looked at his background, he did some really nice work on a program called Skateboards to Starships. And that was from the Royal Institution, also in the UK. So without any further ado, I'd like to ask Satinder to come and join me here on stage, and he'll be talking about mycorrhizal fungi and biobeneficiation for lunar regolith. Thank you.
Good afternoon. Thank you for that introduction. So we're going to be looking at some experiments that were done using JC1A simulant and mycorrhizal fungi, and the lettuce that we were growing, I wouldn't advise anyone to eat it. I don't think it would be edible, but we'll be discussing that further. The association of mycorrhizal associations with soil and with plants is a symbiotic relationship. So for mycorrhizal to function as a biobeneficiation mechanism, it requires a plant for it to keep alive. Okay, so sort of to preface this, the intersection between life support systems, ISRU, space agriculture, that interface is quite an interesting place to be explored. I think over the coming decades, you've got materials that could be recycled between all of these processes, and there could be a role for beneficiation to allow recycling of human waste products, but also plant waste products, and also the waste products from core chemical processing in ISRU. And here we sort of looked at the idea of synergistic beneficiation, defined here as the idea of biobeneficiation coupled with traditional beneficiation methods. So combined, they give a greater effect than the individual processes by themselves. Okay, so mycorrhizal and other microbiota has been used terrestrially in the mining industry to kind of improve the grade of iron ore, for example, removing things like phosphorus and potassium, increases the efficiency before any processing. So there is a case terrestrially where this has been used as a way of increasing the quality of the ore. But also what's found is there's an association there with particle size reduction. The smaller particle sizes give you a greater surface area. So for chemical reactions, they found there was an efficiency. The smaller particle sizes had a better range of association, mycorrhizal associations, than the bigger particles. And this was also observed in experiments we did. So JC1A was screened or sieved into a few different size ranges. So we had 1 to 0.5 micrometers, 0.5 to 0.25, and then so on, 250 micrometers to 125, and then we had 125 to 63, and then 63 and below. And then we had an unbeneficiated sample as well. And then we sort of had some repeats. We were able to have 2 that were with non-mycorrhizal, and then we had 3 with mycorrhizal fungi supplemented there as well. We also had some comminuted samples as well from a different experiment, and so that would have given really, really fine particle sizes. And again, there was issues that happened. Overall, what we found was below 63 micrometers, there was a problem for the plants to grow. And again, the mixing was a problem, compacting was pronounced. And then perlite was used to supplement the regolith itself, the simulant itself, to enable plant growth. Initially, the unbeneficiated simulant did great, as did the 1 to 0.5 particle sizes, as there was less resistance to the seedlings growing. And so those seedlings grew the quickest. The 125 to 63 micrometers took the longest, but we'll see at the end of the growth cycle, they performed the best at the end of it. So Mazzina was chosen because it takes about a 5-week duration for the crop to grow, but we extended the growth time to about 4 months. So we went way beyond. So here's a 14-day snapshot. You're seeing some seedlings are now emerging. 42 days, and the unbeneficiated is doing quite well. We see that the 1 to 5 millimeter particles have the greatest heights because they had the least resistance, but there was some deficiencies in the plants themselves. In terms of the foliage itself, the leaves were not so broad. They had the length, but there seems to be not as much uptake of the nutrients available in the simulant itself. And then at the end of the cycle, roughly about 4 months, and it was these smaller size fractions that were maintaining the mycorrhizal associations, and those plants were still alive. And then the unbeneficiated, which had done great before, at this point was not great. I mean, the unbeneficiated, it has to be remembered, does have that lower size fraction, has all of them as well. But then the best of these were put together, and samples were taken for the best ones. So here you see the unbeneficiated, we see the 1 millimeter to 0.5 millimeter, and then decreasing 0.5 to 0.25, and then 250 micrometers down to 125. Okay, and whoops, go back one. Okay, and then we didn't have anything from 63 below because they took the longest to grow. Again, they had the most resistance, and then they didn't really do well. And even with the comminuted, they began, but then the comminuted regolith, the JC1A, kind of became a sludge, more like a mud. And then it was even with the mycorrhizal, the non-mycorrhizal pots didn't grow at all. The ones with the mycorrhizal did. So below 63 and the community samples, we had no samples after 4 months. And as you can see, and these were removed delicately with tweezers, you can see that the simulant is attached to the roots and the mycorrhizal associations, and the greatest is the smallest particle sizes there. We see how much came off with it, and there's multiple plants, and as we will see now, there was mycorrhizal associations between these roots themselves. Okay, so now some pretty pictures. This was the 1 millimeter to 0.5. And you can see the mycelium growing over the regolith particles, and then there's hyphae penetrating the JSC1A, and you can see the perlite. If we zoom in to that location there, we can see the mycelium clearly that has colonized the plant root, and it is now spreading to the JSC1A particles, and you can see the hyphae there penetrating the bigger particles at different locations. Okay, has to do work because these particles are bigger. If we zoom in a bit more, we can see those clearly, 3 to 4, at least visible there, hyphae that are penetrating the JSC1A to extract nutrients that are important. And then if we zoom into this area here, we can see hyphae there separate, closed in, and see the mycelium growing. Okay, so these SEM images are quite interesting, and they show, again, remember this is after 4 months. If these samples had been taken halfway through the growth cycle, the unbeneficiated would be much more promising. There would have been a lot more mycorrhizal associations. But again, at the 4-month period, we were trying to see how, I mean, it could have carried on. We killed the experiment at that point due to time restrictions, but there was still potentially enough nutrients there to continue keeping those plants alive and for the mycorrhiza to keep extracting nutrients of interest. And we can see the close-ups there of the 125 micrometer to 63 micrometer range, and we see a lot more mycorrhizal associations penetrating the regolith particle, the simulant particle, sorry, but also root to root as well. And you can see in that bottom corner mycorrhizal connections between roots. And again, this happens terrestrially as well. Mycorrhizal are known to form connections between different plants in order to transfer carbon and to serve as a carbon store as well. So it's interesting to see that happening in the smallest size fraction. So although the 250 to 125 was also great, it was doing promising, those smaller size particles just meant less work for the mycorrhizal, and there was more associations built and clearly visible between plants and between the smaller particles, simulant particles as well. Okay, so we can see it close up there, crisscrossing across, and this particular root is of interest, and we can see it optically as well, so you can see two different roots are connecting with each other. In the optical, it's a bit more visible as well, so we can see not only are they connecting to the simulant, but also the roots are, the mycorrhizal hyphae are connecting and making structures amongst themselves as well, between two separate roots. You can have a quick close-up of that as well, so you can see they're clearly crossing over with each other. And there is also an EDS of that same location, which is interesting to see a clear uptake of potassium. Phosphorus signal was a bit noisy. What's interesting here is the iron, aluminium, and silicon. Again, these are micronutrients that are important, but there is also the problem of too much iron being uptaken. Once we create an acidic environment, the simulant itself is alkali, and we expect the regolith to also be quite alkali. So there is an issue there for plant growth, but plants themselves exude organic acids, as does mycorrhizal locally within the root area, substructures there, which creates an acidic environment, which on one hand is great because it's going to help with plant growth, but it's also problematic because too much iron may be uptaken, which is going to be detrimental to the plant health. So here the mycorrhizal seems to protect the plant as well, and this kind of limits how much iron is uptaken. You can see there's a bit of a gap there in the EDS for the iron, which is the top corner there, the dark blue one, and with the aluminium as well. So again, especially the iron is important, but it seems to be protecting the plant root. You can see a clear carbon signature there at the bottom corner, and you can also make out the mycorrhizal roots as well with the carbon. So again, sort of backing the idea that mycorrhizal could be a great carbon store. We can talk about how carbon is going to get there in the first place and the reserves that may be in the double permanent shallow regions, along with other supervolatiles. But however we get the carbon there, or you make use of carbon in situ, this could be one way of keeping the carbon within the cycle. And you can see the acidic numbers, how the alkaline environment got more acidic. The top number there, the JC1A, is before anything was done to it. That's just as it came, pH value there. And then even without any mycorrhizal anion beneficiate, we see a reduction in the pH value, so it's getting more acidic, and that will be due to the plants themselves releasing their own organic acids. And then as we go down and we see finer particle sizes and more mycorrhizal associations, we see an increasing decrease in pH values, and the environment is getting more acidic as we go through that. Okay, so just to summarize, there's a clear uptake of potassium in the plant roots. The decreasing size fractions are accompanied by increasing mycorrhizal and root associations with the JC1A and among plant roots themselves. Decrease in pH level was observed, and subsequent local modification, I should say, of the acidic state, alkaline state of the JC1A through low molecular weight organic anions that are released, and low uptake of aluminium and iron suggested there is a protective role that mycorrhizal plays. It's worth noting that even terrestrially, there is a kind of bargain between the mycorrhizal fungi associations and the plants themselves. The mycorrhizal has no interest in the phosphorus, the potassium, the macro and micronutrients. What it wants is the carbon in forms of carbohydrates or sugars from the plant, from photosynthesis, and it will exchange that with the mycorrhizal, it will exchange that with the plant. Once it receives its carbon, it will release the nutrients. So there is a level of control. It controls how much is uptaken by the plant. And so this protection that it offers is linked with that capability as it colonizes the roots of the plant and it dictates what comes in and what comes out, including water as well. So there's a really interesting association that is developed in the symbiosis between plants and mycorrhizal. So biobeneficiation could be incorporated into space resource ecosystems and the idea of a value chain, potentially pre-processing and post-processing. Terrestrially, it has already been used to improve the grade of iron ores, but there is a use for post-processing, so chemical, for example, waste from ISRU chemical processing, these big core processes, that waste product still has some nutrients of value that could be extracted or used to add some level of circularity and recycling some of the ISRU waste. And also has a role for bioremediation, terrestrially as well as in space. And then one of the maybe more interesting things related to regenerative life support systems could be contribution to pedogenesis cycles. Now, we're not talking about terraforming on a big scale, but within enclosed systems, there is a role that mycorrhizal could play in making the regolith media, if we're going to grow plants in that media, a bit more soil-like. By adding the organic component, the plants that we've shown here, if they're not going to be edible, they would add at least some detritus or biological matter, organic matter to that medium. And so over a few generations, in an enclosed space, regolith that is used could become more soil-like, and mycorrhizal could contribute that along with other microbes in terms of synergistic associations. Okay, so some references here, and I would like to thank you for your time.
Thank you so much. I'm sure this is the domain of Professor Hadler, if she's here, but I'm going to ask you a question anyway. From my understanding is that when you try to deal with the iron ore, you use the fungi for removing phosphorus, no? And quite a few of the papers in the literature, they talk about removing the phosphorus as a main thing. I've seen papers say, yes, it removes it. Others say they don't remove. It depends, I think, on what you're using. So what's your uptake on this? What do you think?
I mean, terrestrially it has been demonstrated for iron ores that are terrestrially, that removing the phosphorus and potassium increases the quality of the ore before processing. You're removing something that you don't care about or need or use, so you're getting a purer ore coming into as an input to the process. In terms of the lunar environment, you could question where is the potassium or the phosphorus coming from. You've got higher isotopes, you've got the lighter isotopes in the regolith, the heavier isotopes in the UR creep deposits. You've got different potential phosphorus sources, so it kind of depends on what source we're using. There is phosphorus and potassium in the regolith itself, but there could be multiple sources, and what this would link to would be relating particle size and potentially modifying particle size as well to make it more accessible.
Okay, here's another quick question for you, because you mentioned at the end that with time, you think the quality of the regolith will improve, that you can actually eat the stuff coming off it. So just bear with me for a sec, humor me here. So how many cycles you think of planting, etc.? I mean, if you have an idea, I mean, I don't know, this is a hypothetical question. If you do this, grow on the same material 3, 4, 5, 6, 7 times, I'm deviating from the subject of biobeneficiation, but will you be able to eat what you're producing?
Well, so again, with the regolith itself, it has things that are great for plants, things that are not great for plants. The experiments we're doing with simulants are sort of lacking in the sense that we don't have simulants that have nitrogen, for example, and in volatiles, then we do believe that there is nitrogen and some other supervolatiles on the moon, not just in the double permanently shallow regions, but also nitrogen has been implanted by the solar wind and the earth wind as well. So again, our simulants, the experiments we do here are lacking that. It's difficult to do that. So moving forward, that'd be something we want to implement. Now, nitrogen is important because it's going to add that structure and then protein synthesis for the plants. So again, these plants are not at the optimal. When we did a control sample with regular soil, the plants were so much taller, so much higher with regular soil. So that is a limitation of that. So in terms of edible lettuce and things like that, The idea of podogenesis, then, it requires that organics to, one, protect the plant itself, and also to remove some of the toxic elements. Plants themselves have been used, and the acids they excrete have been used terrestrially for basically detoxifying toxic elements in soil. So there is a role for plants to play. So it will take a few generations and further experimentation to decide whether it's edible. And again, that's outside the remit of biobeneficiation, but again, it's where we link in the interface between us and the life support systems and the agricultural guys. So there is a case for supplementing media. Now, the stuff we're looking at with Solstice, and please do come to our stand, where we're looking at, in our current study with ESA, where we're actually extracting a nutrient fluid to bypass that element of the nasty stuff that might be in the soil. And again, you've got water efficiency. So I'd say there's a case for supplementing the regolith to make it more soil-like, but there's also a use case to extract the nutrients of value and has some kind of hydroponic fuel as well. So there's a case for both.
I look forward to hearing more about it. Are there any questions in the... we have a question here.
I already got Mike. So, Jakub Ciążela, Polish Academy of Sciences. My question is, why potassium from beneficiation point of view? Because you have alkali elements that are much more abundant, for example, calcium in lunar highlands or magnesium in lunar lowlands, in lunar maria. So what about them?
Right, so yeah, again, the signal, the EDS was tricky and it was limited, what were the signals we could get. So the potassium signal was the clearest. And there was, again, magnesium considerations, but it's just the EDS didn't come out that clear. So in future work, we will be considering other simulants, supplementing the simulants as we can, and it would be great to consider the other things. So even the phosphorus signal was not that clear, but again, it was more about what was present in the JSC1A simulant, and we chose that mainly because it had the widest size distribution, and we were exploring that association of decreasing particle size and the greater associations between the fungi and the regolith simulant particles themselves.
So we will try other elements later also?
Yes, and again, this is something that we are looking at as well in terms of the limitations of the simulants that are available, and I know there's people in this very room that are looking into supplementing simulants with even sort of volatiles and things that are going to be crucial for plant growth. Micro and macronutrients are all important, but I think what the work does demonstrate is that the fungi itself can help protect the plant from the nasty stuff that's in there, or limit how much iron, for example, which is crucial, but too much iron is detrimental to the plant growth. So I think that has been demonstrated. But yeah, definitely moving forward in future iterations, we do want to, especially the magnesium, and there's a range of micronutrients, and we have done some experiments with Highland simulants as well, but we're going to repeat those experiments as well.
Okay, thank you. I think we
thank
can
you very much
afterward. Thanks a lot. Thank you. Thank you. Okay, the next topic, I did mention what it's going to be about. It's about fuel sloshing inside the tank. And it really is another interesting topic in here. And it's going to be presented by Mohammadamin Alandihallaj from the University of Luxembourg, who has got his BSc and Masters and PhD from Sharif University in Iran in aerospace engineering. And then he did his postdoc at the Toronto Institute of Space Studies. And he's going to talk to us about enabling space exploration through in-orbit refueling, a control approach to sloshing mitigation. Please.
Hello, everyone, and good afternoon. In a short presentation in a couple of minutes, I try to give you a different prospect of the space resources. Okay, today we had a different talks and presentation about the importance of the water in a space. We know that if we want to drink something in a space, or want to extract oxygen in a space, or in other planets and somewhere else, or we can use water as the radiation shield. So in one word, we can use water to make a habitation there, but what else? It can be used as a propellant there. There are many companies working on developing different propulsion systems that use water as the propellant that can enable deep space explorations. Why? Because if you have a long journey on Earth, for sure you cannot fill your tank at your home and go for 10,000 kilometers. For sure, on the way, you have to refuel your car. So if you want to go to the best space to explore, you have to refuel on your way. So maybe this water in a space be an opportunity to go beyond. So based on our analysis, it shows that it's not just deep space. Even if we want to explore the other planets, such as Mars, it's better to refuel your launch vehicle or spacecraft around the moon or in Lagrangian points of the Earth-Sun system. But, for example, SpaceX has a different option. SpaceX offers refueling in LEO orbit using Starship. One Starship lifts off, and another one connects to the first one to refuel the first Starships to go to Mars, because they want to increase the payload mass of the spacecraft to the Mars missions. But the most important thing is that for all of these options, we need refueling. And that's why the refueling technology needs to be investigated. So the question is that why it's important in a space. As I said, when you want to go on a long journey on Earth, you just go to a gas station, your car is stationary, the gas station is stationary, everything is simple, you just refuel your car. But in space, everything is different. The gas station and the satellite are moving at high speed, around 8 to 10 kilometers per second. So even a small unwanted movement can destroy your satellite. And the most important thing is the dynamic of fuel in space is completely different from the dynamics of the fuel on Earth. So it's a little complicated, so we need something to mitigate this sloshing and this movement in space. In SNT of the University of Luxembourg, we had a lab called Zero G Lab. It is developed with a collaboration of different research groups, including space system, space robotics, automotive research group, and CVI2, the computer vision research group, in which you can simulate the near real conditions in space. We can simulate docking missions. We have 2 floating platforms there. We have robotic arms there. And we can simulate distributed system and the movement in a space there with a good level of accuracy. So we can use this facility to research on the refueling the space problem. How? We just equip the floating platforms with the tank. One of them is a big tank which works as a tanker, and another one is a small tank which works as a target satellite. And the objective is to control these floating platforms to dock with each other, and somehow that the fuel is not sloshing during the docking phase, because when you make a slosh, and then a slosh makes you some unwanted movements. And those unwanted movements can make some unwanted speeds, and that can destroy your satellites during the docking phase. So just one point, it's not just about the refueling, it can be about the refilling. Because when you talk about extracting water from an asteroid and a planet, you may want to deliver those water somewhere else. For example, you want to deliver the water that you extracted from an asteroid to Earth. So you want to refill your tanker from the extractor in a space. So it's not just about the refueling. It can be a matter of the refilling, even the tanker, to bring something that you have in a space as a resource, like water, to send to somewhere else, to bring it to the Earth or to transmit to somewhere else in space. Okay. As I said, the most important problem is that the dynamics of the sloshing of the fuel. The dynamic of the fuel is very complex, and it can be a function of the technical specification of your satellite, the shape, the size, the mass of the fuel that you have. Your tank is completely full, or is half full, or it's empty. The viscosity of the fuel, the mass of the fuel, the shape of your tank, and even the shape of your satellite, and the place of your propulsion system, the place of the nozzles, and the configuration of your nozzles, and anything. So it's a completely different, it's a completely complex dynamics. So the method that we offer is a combination of a predictive method and an estimated method. Why? Because for controlling, the most important factor in fuel sloshing is the state of your fuel. So, but there is no sensor to measure that state. So we need to estimate that state to be fed in your controller. So we combine a predictive control with the estimator, an MPC, with the LQG, to work with each other to first predict the next state of the fuel in future, and then find a way to mitigate that sloshing. That's the point of the controller. So the controller predicts the future based on an approximated model of the fluid that we have, and then try to move the satellite somehow that the fuel is not sloshed. Also, there are some other constraints that we have to consider. For example, for sure you don't want your satellite collide with your tanker. So there are some inter-satellite collision avoidance constraints. Also, there are some zones. For example, in the lab, we have the lab region that your satellite should be moving inside. And here, with the black borders are the borders of the lab, and the target is to dock with the tanker, with the target satellite, which is green, in the middle of the lab, and the blue one is the tanker that should dock with the target satellite. So the most important one is the accuracy of your movement, of the movement of your satellites, and also the sloshing problem that should be mitigated during the movement. So I told you that we estimate the state of the fuel during the mission. In this figure, you can see the effect of the estimation of the fuel. In two cases, we just control the satellites without estimation of the fuel state, and the first one, we use the data of the estimation. As I said, there is no sensor to measure the fuel state. We have to estimate the fuel state based on the dynamics of the satellite. For example, if your satellite is shifted to the right, you have to know that, okay, for sure, the state of the fuel is something like this, for example. So using the approximate model, you can estimate the state of the fuel inside the tank. As you see, the sloshing, in the first case that we use estimation of the fuel state, is reduced in less than 10 seconds and completely converts to zero in less than 1 minute. But in the second case, no, it continues. And why it's important? The effect on the velocity. During the docking moment, the blue one is the case that we estimate the fuel sloshing state during the docking phase, and the second one that you can see some small movements is the case that we do not use the data estimation in the control procedure. And the point is that those red ones can destroy your satellite if you cannot avoid them. So, in summary, I can say that we need refueling and refilling in a space. If you want to use water as your propellant, or even you want to go to the planetary missions, you need refueling in a space. But the problem is that because of high speed at the space, even small unwanted movement can destroy your satellites. So high accuracy is very important. But the problem is that the dynamic of the fuel is very complex, as it is not possible to use the exact, and there is no sensor to measure the data from the state of your fluid in a space. So the only option that you have is to increase the accuracy of your controller by using the predictions and estimation data using some filtering and the combination of the control method and in a way we just offer one solution, but for sure there are many other solutions. Yeah, that's it. Thank you.
Thank you so much for your presentation. Does anyone have any questions in the audience? Anyone? Yes, there's one at the back there.
I was just curious. A standard way this is handled is with passive slosh baffles. So why did you consider that? And if not, why not?
Okay. The positive of the control field is that always you can say that, okay, I can increase the accuracy. Even now, you can find some papers that work on the controlling of the inverted pendulum. It's clear that more than 100 years ago, this control problem is solved. But even nowadays, we work on the controlling such problems to increase the accuracy. You're right. We can use some passive ways or some traditional controllers, but the accuracy is not enough, or we can offer something with higher accuracy, though, so that's the point.
Thank you so much indeed. Thank you. If you can wait there as well, please. Thank you. And the final speaker in this session is Professor Dr. Matthias Sperl from DLR, who has since 2011 been a group leader in granular matter at the German Aerospace Agency in Cologne. And since 2016, has been a professor of physics for granular matter at the Institute of Theoretical Physics, also at the University of Cologne. And today he'll be talking to us about challenges on the moon and benefits on Earth. Thank you. Building materials.
Thank you much. So I used to give my introduction to school kids that I'm a professor for playing with sand on the space station. So, very envious position. So, thank you very much for the kind introduction. And I have the pleasure today to give you a little bit of an overview of our last 10 years of experiencing playing with building materials for space. And I list, hopefully, not exhaustive, but many of the collaborators we had over the years. And I also wanted to advertise my colleagues who are literally at the hottest exhibition out there producing real fibers from regolith. And they're also showing, which I show on the right-hand side, the Mason mixer we had with Matthias Maher on the space station. So if you haven't done so, pay them a visit later or tomorrow. I also wanted to quickly show you where we come from. So we are sort of a sister site of ESA's in Cologne. And here you see the 1-week-old picture of our lunar habitat that Matthias Maher was already advertising. And one thing I wanted to stress, do I have a laser pointer here? So this is where I am from. So this is the Institute of Materials Physics. And you should see that there's plenty large number of other institutes around on that campus, which will supplement the scientific impact that we expect from the lunar facility. And I will also mention some of the material scientific instrumentation we have here. So if you come to Luna in Cologne, Not all is for free, but we will do our best to make sure that you do a lot of science with us. And we have a legacy of microgravity experience, which you see on the upper left-hand side. We have a brand new transmission electron microscope and several ways of sintering heating for producing volatiles, water, and building materials. In terms of legacy from the space station, and hopefully not underappreciated field is what we have been doing in the last 20 years on the International Space Station. And playing with sand, I show you Samantha Cristoforetti on the left-hand side, playing with M&Ms and making a vital contribution to the extension of the ideal gas law for dissipative granular particles. I show you Alexander Gerst installing on the fluid science lab on the Columbus laboratory a laser scattering device that will also be instrumental for characterizing sand in the exploration context, and with Matthias Maurer and sound and regolith measurements I will continue, and I will also show you that we made a lot of progress, which is on the upper right-hand side, in terms of modeling things better. So here is my first exploration study that we did in 2014 and 15, where we in the end had quite some engineering data from sintered regolith, and you can see it's a very uncommon suit because it doesn't have only the ESA sign, it also has the European Union sign because it was funded by the European Commission. And different from many similar such scenarios, what you have here can actually be built. So there's an engineering calculation underneath of all of those buildings. What do we need to do that? And I show you here the last sort of 10 years where we started with sintering, and our colleagues from the US, namely Alexander Radlinska, started with concrete. We had almost a mission every year, and we were sharing and exchanging data, and we were migrating towards doing cement and concrete. And the last point we had was Matthias Maurer's mission with the Mason experiment. And for those who are not familiar with the German term for Mason, it's actually Maurer. And what we did is we invented the name for the instrument first, and then came up with an acronym that Mason stands for, which was quite puzzling for some of the German journalists. Now, so the clicker really needs some other battery. Here is what I had the pleasure to do with Jerry Sanders. So he was inviting me to that ISAC-G meeting. And we had, in the end, numerous discussions about little tiny issues. And I saved myself from showing one of those complicated diagrams. I remember one discussion where I always felt the European view of sustainability may be different from the American one. So we talked about landing platforms, and an American view of a landing platform being sustainable is it's there for 100 years. The European one is that it's gone after you used it and then you don't need it any longer. We had quite some discussions about stability, the utilization of the soil we wanted to live from. And one Earth-based example, and I have 3 of them, is concrete. And you should appreciate that 8% of the CO2 humankind is evaporating into the atmosphere comes from building. Most of it from cement, producing cement, handling cement, heating cement. And it's usually not a straightforward one topic issue. So you cannot say, here is the single point where I have to interfere. Actually, there's a very readable review where you could see that all the way the process chain, you could save energy, you could save CO2, you could make improvements by making experiments and better modeling. And in a number of that stages, you can benefit also from microgravity experiments. Here's my favorite, analyzing some granular packing, also producing cement and looking at the hardening of that substances. So we did the investigation, and I'm not going into the details of what we have is 64 samples. But one executive summary could be that for specific compositions, we can prove that you can, by allowing the sample to harden in the most efficient way, save 20% of cement, because you gain 20% better yield stresses in your material if you do it in the homogeneous environment in microgravity. You also get more bubbles, which is not necessarily what we wanted, but that's a beneficial effect. And we are currently considering how we would convince an earth-based concrete to do the same thing on Earth and allow us to save those 20% also on the ground. We have a mission coming up in September where we replace the cement that successfully demonstrated that we can make lunar concrete. We replace that by geopolymer, and the geopolymer has also some benefit if you use it for concrete on Earth, because it saves CO2, and it saves something very important. If we use it on the Moon, it saves water. Here is unfortunately a video I cannot show, but this is our solar oven in Cologne, where we come in with roughly a coin-size spot, and we are able to do 3D printing without too many other pieces of equipment except for the solar radiation that we're using, and we can convert that little heap of regolith very reliably into a piece of brick. There's one thing we learned, that we do not want to use the actual sun, because the atmospheric fluctuations on Earth, even on a sunny day, are enough to destroy the stability of our control for heating the sample. But if there's one thing we don't worry about on the Moon, is that we have atmospheric fluctuations. So what we're using as a simulated sun is those cinema lamps, and with the brick being in existence, we can also use it for many other uses. In addition to just a stability of a habitat, we can use it for heat storage, and certainly for radiation shielding, and for the mechanical stability of buildings if we heap on top of it many more tons of additional regolith for radiation shielding. Here is what I mentioned before. You can also use regolith for tensile stability if you produce a fiber, and you could nicely see that outside. You pour in some of your regolith, you pull it into a fiber, you wind it up, and then you can use it for a textile. And one approach that's currently going on in a PhD thesis is increasing the tensile strength of both binder-based and sintered materials by adding some fibers to it. Here is something I'm not going to explain, but just to appeal to. We learned on the talk before that even if you have the right equations for the fluid behavior, it may be difficult to describe something as complex as sloshing. Here I wanted to make a brief appeal that we want some theoretical foundation for doing rheology with grains. And if you have not heard the story, I tell you now. On the upper right-hand corner, this is humankind's first extraterrestrial experiment in rheology. So Aldrin was not only asked to leave a footprint for the history books. So this was actually a question of how cohesive, in a rheological sense, the lunar soil would turn out to be. And you see by the sharp ridges of the footprint, which is counter to what you see if you go to the beach where the sand is flowing, that you have quite some cohesion among the lunar soil. And I only wanted to appeal to my experiments here, where you have so-called flow curves. that have on the horizontal axis the shear rate. So this is how strongly you stir your grains. And on the y-axis, you have the shear forces, the shear stress. And what you should appreciate, the data is the points, and the theory is the full lines. And you can nowadays describe over many, many orders of magnitude the shear behavior of grains in motion. And you can also qualitatively characterize that in terms of shear thinning, shear thickening, Newtonian behavior. And I give you the full reference here for keeping you busy all night. But that is also what I would call a benefit of us dealing with building materials. So I stole something from the second line of Kennedy. So how do we go to the moon and do all the other things? I wanted to advertise that we use some of the legacy we have from the ISS. So there's brilliant people investigating things that are having a gravity dependence. One benefit for Earth is that you have better in situ diagnostics that will also benefit process monitoring on Earth. We have better modeling, which I think is a good return to the community on Earth. We do have bottom-up approaches where we take into account people from the different fields. I think that's a no-brainer for people here in that room. Also involving non-space actors to really make the next approach to the moon a very broad one. And certainly we would also use technology spin-in. And with that, I wanted to leave you with a slide puzzle, and thank you for your attention.
Thank you so much. I mean, you covered a whole wide range of things, you know, from concrete, regolith, to gravity, microgravity. I'm sure there'll be some questions in the audience. Does anybody have any questions? Because if not, I'm actually fascinated, because you very briefly touched on it, that you formed that little briquette from regolith. Do you have any ideas about the tensile strength of this compared to the tensile flexural strength of concrete, for example? I mean, these are important issues.
Yeah, we have an idea because we measured all of it. So the final strength of what you can do with sintered regolith or regolith you use with Portland cement is identical, or mostly identical, to what you have for concrete on Earth. Wow. So current technology for additive layer manufacturing has the problem that about every 50th layer, you get some weak layer because you have variations in solar power, you have variations in the used material. So if you want to make a comparison to a material on Earth, our results a couple of years ago for the sintered version of regolith is roughly gypsum. So this is about a factor 4 or 5 weaker than a decent concrete, but that is some refinement you would probably do for emission.
So about 60 pounds per square inch, roughly, then? Because concrete's like 600 or something like that.
Yeah, so I need to do the multiplication with 15, but
okay.
So but I could do it in megapascal. The tensile strength we try to add with the fibers. Yeah. So the idea is to have the equivalent of steel reinforcement. Yeah. Otherwise, which you see in those nice scenarios, we're building like the Romans. Yeah? Okay. Romans, having invented concrete, also built in a way that you always only have pressure and not tensile strength.
Wow. Romans on the moon. I have another question, which I'm sure many other people are thinking about it, but they're not asking it, is how do you get to put your instrument on this space station? What do you have to do? I mean, you're one of the lucky people who do that.
Well, it's like always in science, you work hard in the lab, then you have an idea that you need microgravity, and then you write up a proposal. And then you hope people read your proposal and rate it favorably. At DLR, we have a couple advantages, and I mentioned only 2 of them. So I started out my career as a statistical physicist, and I really migrated into becoming a rocket scientist because our institute has their very own rocket for doing one launch every year, and we have about 5 to 10 experiments on such rockets. If you have an idea that needs 6 minutes of microgravity time, talk to me. But inviting me for a dinner doesn't help. We evaluate it very strictly. Also, I had the great luck of being on the ESA DLR mission team for a couple of those educational payloads we had for many of the crew members in the recent astronaut corps. And that really helped to bring simple experiments on the space station. And the original design for that concrete experiment only had 2 syringes. Yeah? You also need to do things a little cleverly, because earlier there was a space shuttle experiment also dealing with concrete, but they had the unfortunate idea to only separate water and cement by a membrane. And you can guess from my introduction to that problem, the membrane broke at 6G on launch, and they had a very nice concrete block already upon arrival on the space in orbit. But I think there was another question I saw. Yeah.
Yes, I have the mic already. So it's Jakub Ciążela again. My question is, have you already had an opportunity to test your concrete to strong temperature changes expected on the moon?
We have, to my knowledge, not done that with concrete samples we got from the space station, because they are very precious. We do all the non-destructive tests before we do the destructive ones. And unfortunately for me as a physicist, engineers in the end want to destroy everything to show what the ultimate strength is. We did a lot of thermal cycling for what we did on ground with sintered bricks. And I assume you're targeting the very problem of a matrix material like concrete. You have embedded, by the very nature of how you produce the material, different thermal expansion coefficients. So this was basically why we, in the beginning, went for the artificial rock done by sintering, which can be more robust than a matrix material like concrete. And I'm pretty certain if we thermally cycle our concrete samples that they would break before the comparison with sintered bricks.
Okay, thank you very much.
Any other questions in the audience? If you have time, there's a fantastic video on YouTube of Professor Sperl describing what happens to particles under vacuum, not under vacuum, under zero gravity. It really is. It's produced by some Belgian the science program or something. I can't remember, but it really is well worth looking at. Just search the name on YouTube, and you'll find that video over there. Does anyone have a question to our speakers? I mean, you've had time to think about it. We've discussed some really interesting topics. We've discussed nuclear power, we've discussed fungi, we've discussed fuel tanks, we've discussed building things in space. Does anyone have anything we can close with before? I know you're all desperate to finish, to go to the cocktail afterwards or the next session. But if anybody has any questions, we'll be delighted.
Yeah. I have the mic if I can speak.
Yes, please.
Here. I'm here. Okay, so my question is to Satinder, basically. On this side, if you guys are searching for me, on the left, or your right, maybe. This side, I'm standing. Here. So basically, my question to Satinder was that, first of all, thanks for your insights over how fungi can help the plant growth. Just to give you a disclaimer, I'm not a biotechnologist, so pardon me if my question is not as per your standard. But I wanted to know, if you have conducted this test in reduced gravity environment, or are you planning to? And do you think that can affect your fungi itself and the advantages which you think it can provide to the plant? And my context of the question comes from an article which I was going through while listening to your presentation, which says that they conducted a simulated zero-G environment, and a test similar to you, and they said that it negatively affects the mycorrhization and plant phosphate uptake by inhibiting the hyphal elongation and secondary branching. So I wanted to know, like, what is your opinion and insights on the same?
Yes. So yeah, that's a great question, and then it's something we had considered. Again, this study was more about the dependence and the association with reducing particle sizes and how that increased and helped the mycorrhizal itself, and the idea of synergistic biobeneficiation, so the idea of two different beneficiation techniques coming together. But yes, a reduced lunar gravity environment would be something we want to test. And I am familiar with the paper you mentioned, so that is an issue. Again, mycorrhizal is native to this planet, and it has associations with most plants. So putting it in a different environment, which is never experienced, is going to be problematic. And I know of ISS experiments and mycorrhizal being flown for that very reason. So I would counter that, again, if you gave it time, it could be argued that maybe the mycorrhizal could get used to that environment. I would consider it maybe it's a shock to the system because it hasn't experienced that. And again, it is detrimental. We do want to have those mycorrhizal roots and associations as widespread as possible. So that is an issue. And I would say, yeah, if those experiments could run for a longer time, it would be interesting to see, does the mycorrhizal adapt to that lower reduced gravitational environment? What I would say is that in terms of the plant itself, the capillary action, depending on how we water the plants, the capillary action would be more pronounced on the lunar in a lower gravitational environment. So how we water the plants would also be interesting. But yeah, that is something that needs to be focused on in future iterations of this work.
Thank you so much for that answer. And I think we really have to stop now, because otherwise I've been threatened that I'll never be ever invited again if I stop at this stage. I mean, I'm sure you'll join me in thanking such a wonderful group of people. They gave some fantastic presentations. And thank you so much for being here today. Now, bitte schön. Thank you.